last and not least speaker of this session, who is Laurine Duchesne. So, Laurine, you can already unmute your microphone and share your screen while I introduce you. So she's a PhD student at the Montefiore Institute of the University of Liège, Belgium. Her research is about machine learning for short-term operation planning. So, Laurine, I give you the floor.
Yeah, I'm trying to share my screen. Oh, I need to quit Zoom and to redo it.
Okay.
Ça marche. Oh, okay, now it's working. It will work, I hope. Can you see my screen? Screen? Okay, cool. Okay, so hi everybody, I'm Laurine Duchesne and I'm going to present you the paper Machine Learning for Ranking Day-Ahead Decisions in the context of short-term operation planning, which is joint work with Efthymios, Antonio and Louis.
Myself, I don't see your slide now that you have put your viewer on full screen, so something went wrong.
Okay.
So for the sake of time, just escape from the full screen presentation to the normal presentation, I mean to the PDF view.
Okay, does it work now? Can you see?
Okay.
Okay, sorry. So what's the ahead operation planning? In the ahead, the operator has to take decisions in order to enable operating the system within reliability targets in real time. So in the ahead, the decisions can be, for instance, postponing a planned maintenance or adjusting the market clearing outcomes. The day-ahead decisions must be such that the probability of being able to satisfy the reliability target the next day is high and the induced expected cost of real-time operation is low. By induced cost of real-time operation, we mean the cost of the recourse actions the operator has to take in real time in order to adapt to the realization of uncertainties, such as demand, renewable generation, or forced outages, for instance. But the question is how to choose a good decision in the ahead. Oops. So let's assume the operator has a list of K candidate decisions. So the decisions can be, for instance, a unit commitment and power level of generating units, but they could be other things. One way to choose a good decision among this list would be to evaluate for each decision the expected next day impact, considering the various exogenous uncertainties, and then rank the decisions accordingly. And to evaluate the expected next day impact, one could use this method. So if the operator has a generator of plausible next day scenarios and a simulator of real-time operation, it could use the crude Monte Carlo approach in the following way. So for a given decision I, it would generate multiple real-time scenarios, and then for each of them simulate real-time operation. And that will give him, for a given, that will tell him if that scenario with that decision was reliable in real time, and also the cost of the recourse actions. And if you average these values over many scenarios, you can have, for the given decision high, an expected level of reliability and unexpected real-time cost. And then, for instance, if you consider only the expected real-time cost, you can rank the decisions in crescent order of the cost and identify the decisions in your list that had, for instance, the lowest expected real-time cost. But this approach cannot be used in practice due to the computational burden. Indeed, even if you use more advanced techniques than the crude Monte Carlo approach, such as variance reduction techniques, simulating real-time operations still takes a lot of time. So in this paper, what we propose is to replace the real-time operation simulator by a machine learned proxy of real-time operation, And we want this proxy to be able to generalize to new unseen candidate decisions so that it can be used for new decisions. And then we want to use these proxies to rank the candidate decisions in order to pick a good one. Okay. So here's our methodology. So we propose to build a proxy with supervised machine learning. So in supervised machine learning, you build a function that will map the inputs of a database to the outputs. And in this paper, we use the feed-forward neural network algorithm. So we need to build a database. We have a list of candidate decisions we want to assess, and we can generate multiple scenarios. And so what we will do is that for each couple candidate decision real-time scenario, we are going to simulate real-time operation in order to have the corresponding cost. And at the end, our database will contain as inputs the values describing a decision and a scenario, and as output, the corresponding value of the cost. So generating multiple scenarios is easy with a scenario generator, but how could we generate automatically several decisions in order to test our approach? In this paper, we use the following method. So let's assume we want to generate automatically K candidate decision, K the head candidate decision. We start by generating N larger than K real-time scenarios. So there are the blue points here. And they are generated with our real-time scenario generator. And then we apply the K-means clustering algorithm to obtain K clusters. So for instance, here 4 on the slide. And finally, we use the K centers of these clusters as forecast scenarios. And so what we do after that is that we apply to each one of the K forecast scenarios a unit commitment and economic dispatch program in order to obtain at the end K the head candidate decisions. And so at the end, what we have is a database that looks like this. So each square here represents a couple, the head decision next day scenario. And since we want to test if our proxy can be used to unseen decisions, we divide our database in the following way. So the white matrix here is the part of the database used to train, to learn our proxy. And then the 3 blue matrices are used to test our proxy. This matrix here is used to check if our proxy can generalize to unseen scenarios, but seen decisions. The matrix here is used to check if our proxy can generalize to unseen decisions, but seen scenarios. And finally, this matrix here is used to check if our proxy can generalize both to unseen scenarios and unseen decisions. And so if we can show that our proxy can generalize to unseen decisions, we can then use it to rank our list of candidate decisions. And we do it in the following way. So first of all, we are going to select X, the head candidate decisions at random, and we simulate real-time operation for this decision and a certain amount of real-time scenarios. The number X of selected candidate decisions must be such that it is large enough so that our proxy can generalize to new decisions, but not too large since we want to avoid as much as possible using our heavy real-time operation simulator. So then we have our database, and so we use it to learn our ML proxy of real-time operation, and we exploit this proxy to estimate the real-time operation costs for a certain amount of scenarios and all the remaining decisions that were not used to train the proxy. And at the end, we can compute the estimated expected real-time operation cost of each decision simply by averaging the real-time cost over the scenarios for all decisions. And so we can rank the decisions according to this estimated expected cost and identify the decisions with the lowest expected cost. So that is what we propose in the paper, and we tested it on the 3-area IEEE RTS 96 system. We used, in order to generate our head candidate decisions, a unit commitment and economic dispatch program with the N-1 reliability criterion. And our real-time operation simulator is a security constraint optimal power flow with the N-1 reliability criterion. We use the DC approximation, and our recourse actions in real time are preventive and corrective redispatch, load shedding, and wind curtailment. So First, before using our proxy to rank the decisions, we want to know first if it can generalize to new decisions, but also how many decisions are necessary in the training sample in order to have a good proxy. And so it's what we do with that experiment, we test. We selected first 5 decisions, the blue one, at random, and these decisions are never used to train our proxy. They are only there to test it. And first we start by selecting one decision and we learn our proxy with one decision and then we test it on the 5 blue decisions. After that we select 2 decisions, we learn our proxy with 2 decisions and we test it on the blue decisions. And we do that until we consider all decisions except the blue ones to train our proxy and we test it on the blue ones. And here are the results we obtained. So in order to assess the performance of our proxies, we use the R2 score, which is a score such that it is equal to 1 when all the samples are perfectly predicted. Okay. The blue line here corresponds to the case where the decisions are unseen, but the scenario are seen. And the orange line corresponds to the case where both scenarios and decisions are unseen. And if we look at the blue line, we see that with only 5 decisions in the training set, we can already reach convergence with a score close to 1. And so we can already say that in that case, only 5 decisions are necessary in the training set to have ML proxies that can generalize well to unseen decisions. And we see with the orange curve that when for unseen scenarios, we need a bit more decisions in the training set to reach convergence. But we already have a score that is not too bad. And so we can use it to rank our decisions, and it's what we did in the paper. And here are the results. So in this column, what you have is the ground truth. So we estimated the expected real-time cost with our heavy real-time operation simulator on 600 scenarios. And the results are in million euro. And the 2 columns here show the results when we estimate the expected real-time cost with our proxies. This column corresponds to the method I explained in this presentation, and this column corresponds to a variant. You can find all the details in the paper. Okay. And these 2 columns were obtained with 2,000 unseen scenarios. So we used 5 decisions to train our proxy in that case. It's a trade-off between good generalization properties and avoiding as much as possible using the heavy real-time operation simulator. And what you can see is that the ranking is represented with colors. So whiter means less expensive and bluer means more expensive. And you can see in the both cases that the less expensive decisions are identified, as well as the most expensive one. And this method is even better than the previous one. So in conclusion, we show with an IEEE RTS96 test case that our machine learned proxies are able to generalize well to unseen candidate decisions and can be used to identify candidate decisions with the smallest real-time expected cost. And in the future, we plan to extend the methodology to rank several candidate decisions based on the probability of meeting the reliability target, or a combination of probability of meeting the reliability target and the expected real-time cost. And we also plan to reverse the problem in order to find what forecast scenarios would lead to a good day-ahead decision. Thank you for your attention. I would be glad to answer to your questions if you have any.
Thank you, Laurine, for your presentation. Well, we are more or less reaching the end of the allotted time, but since the next session is starting only at noon, and we lost a little bit time with the logistics here, I think we can take a couple of questions also for you. So the first question is about, let's say, what does the approach bring? So for training a proxy, we need to run a real-time operation simulator many times.
Yes.
How is it possible in practice, given the short time that operators have for day-ahead decisions?
The plan is to build it not every day, but to have proxies that can really be used one day to another, and so to avoid having every day to build that database.
Okay, so the second part of this question was why not to apply this RTOS directly on the smaller number of scenarios and use it directly for the evaluation of expected cost for each decision candidate. If you want to comment on that part as well.
I'm not sure I understood. You mean only use the forecast scenarios?
Well, he says, why not to apply this real-time operation simulator directly on the smaller number of scenarios, rather than, I think you have replied to the question, but okay. And then there is one last question. What happens to your method if you have infinite or much larger decision set? So this is about generalizing in the set of decisions. And since you showed results only with, I don't know, 20 or so many, do you think this can generalize to much larger set of candidate decisions?
Yeah, it depends really on the time it's necessary to estimate the expected real-time costs. So with a proxy, in our case, we showed that it can be 10,000 times faster than using the complete scope. Okay. So I would not say it can directly generalize to infinite numbers of decisions, but at least a large number of them, yeah.
And then maybe one final question is the following. If the system changes, meaning new plants or some plants which are getting out of operation or some maintenance activities, is it feasible to train a new proxy rapidly by taking advantage of, let's say, previous proxies, somehow to use transfer learning?
I think it can be possible. So for example, for plant maintenance, it would be useful to first learn the proxy considering the network topology, at least the line and generator status. And then, I really think transfer learning is a good approach for adaptability in power systems.
Okay, thank you, Laurine, for the answers. I think we need to shut down this session. So I'm showing my camera to thank everybody, especially the speakers, of course, but also the technical support team and the audience for this one of the two first regular paper sessions of this PSCC, which goes through the internet rather than a physical meeting. I thank everybody, and I would like to encourage you to continue discussing offline through whatever channel about these interesting research topics. Thank you, everybody, and I say bravo to the speakers.
Thank you.